Good afternoon, everyone. It's a pleasure to be here. My name is Aaron Dialwis. I work in Cisco's SP architectures team focused on IP optical solutions. Thank you for taking time to join us today for this session. I wanted to give an overview with regards to what are the optical transport solutions that are primarily targeted at providing the best and optimal solution for efficiency purpose specifically for IP services. I'll start off first with the usual traffic charts, and primarily the messaging here is the bulk of the traffic and services being carried over service providers' networks today is IP. And I think this is not so foreign to all of us here. This is what we live. This is what our lives every day contribute to. We are all part of this in escalating and making the traffic actually swell in terms of the traffic that's going over the service provider's infrastructure. And the Cisco VNI traffic projections actually substantiate this. There's a huge traffic volume which is expected moving forward with an annual growth rate of about 26%. So the questions that service providers actually ask themselves is that how do we actually scale the transport infrastructure to actually absorb this kind of scale while making sure that we adhere to the strict SLA requirements? How do we scale the network and absorb this kind of traffic volumes while recognizing that you're not actually getting all that much revenue? And again, this makes reference back to the chart which Muthu was sharing earlier about how the revenues are not actually growing, the capex is not actually growing, but at the same time, you have to provide for infrastructure to absorb this kind of traffic. So we all know that the traffic is IP, but is the infrastructure that service providers are building, is that essentially optimized for IP? And I think there's a lot of room for improvement, and this is what I will focus in on for this session. So if we visit this, the next slide, we basically see that the transition between the infrastructure from 20 years ago, which was largely driven by voice switching, to the central offices of service providers today, which is more focused on transport for packet services. It's largely comprised of virtualized elements running on compute, which is being serviced by an IP-based infrastructure. And this kind of scalability is being facilitated by advancement in IP, in terms of providing a transport paradigm onto IP-based solutions, and innovations such as segment routing, which provides more efficiency for transport solutions across IP and MPLS-based infrastructure. At the same time, as you can see, the standardization has proceeded beyond the 10G phase for packet, and we have now standardized interfaces for 100G, and moving forward, 400G, and higher bandwidths, port bandwidths beyond that. Whereas if you look at where TDM has come from, we are pretty much, there hasn't been a lot of innovation in TDM. And the only big innovation, I would say, was the introduction of the OTN standards, which essentially was there to provide transparency for legacy SDH SONET systems. And the innovations that you've heard with regards to OTN has merely been to serve or to address the granularity problems which is inherent within OTN, which is not present in IP and PLS, for example. So with that in mind, recognizing that the bulk of traffic is IP-based, and the granularity problem within OTN, and the scalability which IP and MPLS already provides today, I wanted to provide you a view with what's essentially wrong with the architectures that we have in a lot of service providers' network, and what are the kinds of solutions that we see will address these limitations or remove these limitations and allow more scale and efficiency in the optical transport architectures of service providers. Let's start off with this view, which essentially is a representation of the siloed approach of service providers. You have typically, within any service providers, you have an IP-focused team, and then you have a transport-focused team. And these two teams don't necessarily talk seamlessly or transparently with each other. And fundamentally, the service handoff between IP and transport, there's redundancies engineered into each of the service demands. So the IP layer has engineered some resiliency capacity, and this gets handed off to the transport domain, and then the transport domain applies on additional network resources to make sure that you have, for example, restoration and protection switching facilities. And this is primarily because classically, it was cheaper to transport on optical infrastructure, and interfaces on the routing layer was viewed as being more expensive. Certainly, this was true 10 years or so ago. So the function of the OTN switch here is essentially to provide aggregation of largely 10G services and share and carry that efficiently over 100G coherent interfaces on the optical infrastructure. And there's been some improvement in that OTN switches have started to support coherent interfaces as well, directly on the platform, right? So essentially, you see still the same limitation in that you have this protection over protection, which consumes a lot of network resources just for the sake of end-to-end protection across IP and optical. So it's not an efficient utilization of your resources. And over time, because now we have router line ports which are in the order of 36 or 32 100-gig ports on a single line card, now we are at the stage where it is no longer true that it's cheaper to carry services over the optical infrastructure. Now the converse is true, that it is cheaper to carry services on the IP layer because we have much more scalability, and I'll provide more details in a subsequent slide. We have more capabilities to carry more 100 gig and beyond on a single line card compared with what is typically supported on transponders or OTN switches moving forward. This is where most service providers are today. They rely on OTN switching essentially to provide, number one, aggregation of services at potentially at 10G or even lower than 10G. But the question is, does that really provide a lot of value, recognizing that most router ports are going to 100G and beyond? And also, the function of OTN switching was initially to support fast protection switching for all failure scenarios. There were some failure scenarios in where the IP using RSVPTE, for example, for fast reroutes could not converge. But with segment routing, this has all been resolved in that segment routing with TI-LFA provides you guaranteed protection switching resiliency end-to-end at the IP layer. So you don't really need to resort to protection switching on the OTN layer. So there is value in, I would say, in simplifying the architecture, where it's not necessary to incur the costs and complexity of an OTN switching infrastructure, and essentially to leverage IP, leveraging segment routing with TI-LFA to do end-to-end protection switching, and integrating coherent interfaces directly on your routing infrastructure. So we have dedicated line cards today that support what we call an ACO, analog coherent optical pluggables, which allow you to terminate coherent interfaces directly on your routing devices. And that means that you don't rely on line cards on your on your OTN switches or even on your ROADM layer, and basically you have a more simplified architecture in terms of the carrying IP services end to end. And we're enhancing that further with DCO, digital coherent optical interfaces. The difference being with ACO, you have the analog component on the pluggables, and the DSP component is hosted off the line card. With DCO, you have both the coherent transceiver as well as the DSP on the pluggables itself. So as you can see, this greatly simplifies the architecture of the IP optical transport node. So initially, as you can see, I'll try, over here, you can see that there's a lot of line cards which were, keep pressing the wrong one. So initially, as you can see here, there's a lot of line cards, and these represent a lot of configuration stages. And what we've done is effectively removed the layers and the line cards, and this resulted in a very streamlined architecture that you can see here. And in this case, what we're actually doing is improving the densities that we're getting in terms of coherent interfaces on the router. So this is somewhat in the future. This is what we're working towards. And this is IP over Ethernet over fiber that Muthu has introduced in his session. And the nice thing about this solution is that we are driving much more density in terms of getting coherent interfaces on pluggables like QSFP. So in our current solution, we have a DCO, and this takes the form factor of a CFP2. So it's physically larger. So we are expecting some deloading in terms of the port densities that you can get with DCO. Next year, with leveraging 400G ZR solution, we have a much smaller form factor, which will allow us to plug coherent interfaces directly on router line cards without any sacrifice or reduction in port densities. So this gives you a very, very scalable solution in that you don't need to have a dedicated coherent optical interface. Any router line card can flexibly support either gray or coherent interfaces, and the coherent interfaces scales from 100 gig to 400 gig coherent or gray in a very flexible manner. So what this is the message that I want to convey to you is that with this journey, what we are planning to do is simplify the optical infrastructure from a many-layered, siloed approach to something which is very, very streamlined. There's more to this architecture than basically I have time for. This requires a workshop in itself. What we're trying to also convey to you is that this offers you opportunities to simplify the optical layer, right? You can leverage IP as a single aggregation layer to optimize the wavelength field utilization so that it can be more cost-effective to transport and to aggregate your services on IP, which means that you don't need to incur the cost and complexity of router bypass on the optical layer. Therefore, your optical layer can be very simple. Instead of a multi-degree ROADM, you can think of simple point-to-point architectures with just simple filters and amplifier. And everything in terms of routing, aggregation, will be done on the IP layer. Okay? And as a consequence of that, what happens is that as you reduce your layers, all these layers of line cards, you basically reduce and simplify to a single switching element, which is already very much automated. So you can leverage the full automation of your IP on the routing layer to drive even more automation and time to market. So in summary, that was a very loaded slide, and there were many, many points to cover. I'll be more than happy to deal in greater detail on offline sessions with you. But in summary, what we're going after is a much leaner architecture, recognizing the fact that, as we mentioned already, we need to scale the network. At the same time, we need to keep CapEx low because revenues are not improving. And the way that we do that is by delayering, removing all the unnecessary layers in your network, recognizing the traffic is going IP and it's going 100 gig and beyond in terms of granularity. And we leverage segment routing so that you have end-to-end protection across your IP and optical infrastructure without incurring the cost and complexity of an intermediate aggregation layer such as OTN switching. The infrastructure should be scalable. It should be ready for 200G and beyond. And there's the current development, state of development with DSPs are such that we can already support scalabilities to 600 gig, 800 gig, and even beyond. And we should leverage the simplified architecture to promote even more automation, to drive even more automation in the network infrastructure. And last but not least, by removing unnecessary layers and optimizing the physical assets of the networking resources, we reduce CapEx as well as OpEx in terms of footprint power, and basically allow you to get the most out of your fiber infrastructure. Okay. So what is driving the IP convergence? So there's three key applications here, three key considerations. The first being with 5G, as you are all aware, with the user plane, the control and user plane separation, and the move towards having more content and compute moving closer into the aggregation space, closer to where the subscribers are. This has an effect from an optical perspective that more traffic is being generated and consumed at the same time within the metro. So this was very different from the previous architectures where everything was backhauled to the core and to reach content within the core network infrastructure. So now we see the bulk of the bandwidth will be in the metro and reside within the metro. And here the challenge is that because metro distances are shorter, you need to have a means of trading off between the performance and the span. If I don't need to have, the scale and the performance. So if I don't need to go over long distances that typically is in the core, for example, can I leverage or trade off that distance with even more capacity? And traditional transponder and optical solutions don't allow you to do that, unfortunately. So we need to leverage the next generation of DSPs that allow you to flexibly trade off between the scale and the performance, and I'll speak more about that subsequently. So that's the first thing that is a key consideration. Secondly, as you know, with 5G services, there's a huge drive for bandwidth and capacity that needs to now be to consume the cloud RAN resources. And we are basically facilitating that in a very efficient way by using coherent pluggables to extend bandwidth in terms of 100G and 200G to the RAN space. And also in the near future, 400G coherent pluggables will facilitate an even more scalability in the RAN space. And last but not least, the current gray optical standards for 100 gig transmission doesn't support scalability or optical reach beyond 40 kilometers typically. And the DCO coherent interfaces offer you much better scale. So if you're interested in carrying 100 gig over fiber infrastructure, this already can give you additional spans, additional reach performance that go beyond 40 kilometers, typically 70 to 80 kilometers for 100 or 200 gig applications. So essentially, these are the three considerations that we will provide more details towards. So in the metro, very quickly, this is typically how service providers provide the end-to-end services. In IP domain, you have an aggregation router, for example, here. You have a transponder in your optical gear through a filter and amplifier system. And this transponder basically takes a coherent line interface and translates that to the gray. So this is plain vanilla transponder solution. What we are actually proposing is that the coherent interface here can actually be supported using coherent pluggables, which go directly on the aggregation layer. And therefore, it removes the need for expensive transponders. This represents a CapEx and OpEx, right? So this is complexity, costs, and inefficiency, which can easily be replicated by carrying a coherent interface directly on the routing device, on the aggregation device here. Alternatively, if you're fine with carrying 100 gig or 200 gig services directly over fiber, you can choose to carry coherent interfaces over fiber, direct fiber access without DWDM infrastructure. And this typically gives you 70 kilometers for 200 gig or even 80 kilometers for 100 gig coherent interfaces. So primarily, these are the use cases that we are going after for direct coherent interfaces on aggregation devices. And this is a use case. This is Airtel, Bharti Airtel in India. And this is an example of the build-out, the network build-out that they have in the state of Maharashtra. This will be extended nationwide to the whole of India. And essentially, in the aggregation space where this is being deployed, you have aggregation collector rings terminating on NCS 55A2. And the aggregation ring or collector ring serves to aggregate services coming from the access for mobile backhaul as well as fixed broadband customers, and terminating all these service flows into the service edge represented by ASR 9K. Again, all these links in this collector ring that you see here, these are all based on DCO optics. And they're carrying this over fiber, over third-party DWDM. So you can, as I explained earlier, you can connect the coherent interface on existing DWDM infrastructure from any other vendor. And this is being done in a big scale with Bharti Airtel. Currently, they are carrying 100 gig services, but they can carry 200 gig leveraging 16 QAM modulation scheme by just applying a software upgrade. There's no hardware augmentation required to turn on 200G services on this infrastructure. So so that's a very typical use case, right? You have 100 gig rings or single 200 gig rings terminating between aggregation nodes and edge nodes or PE nodes. And that's fine if you have single rings, because we will be the first to admit that with CFP2 DCO, this form factor, which is a bigger pluggable, there is something called IP fabric deload. So there is a lower density in terms of the number of ports that you can support on a single line card. And we are addressing this, as I mentioned, with a more smaller form factor, a QSFP form factor, which can support up to 400 gig coherent interfaces. And this will allow you to support coherent interfaces on line cards without incurring a tax or incurring a lower port densities of your routing infrastructure. So this is pretty much where we are with in the metro, in the access and the metro application. I want to talk to you about, sorry, just getting used to this. talk to you about solutions that we are driving in the core. So in the core, we are looking at a whole set of a different kind of requirements. In the core, the distance is key, and bandwidth is also key. And you typically have this infrastructure, as I mentioned earlier, you have a very scalable IP domain and a very scalable optical photonic domain. And the numbers here, I've considered a 10-degree ROADM, right? And as a legacy from the OTN days, you typically have an OTN switch to aggregate your services, your 10G services, into your coherent interfaces. And in the market, I think the largest OTN switch has a capacity of 25.6 terabit. It features a slot capacity of 400 gig. But the current and in the future DSP capabilities will span beyond this to cover 600 gig, 800 gig, and 1.2 terabit capacity per line card. That will not fit within this architecture because the backplane of this OTN switching infrastructure will not allow a seamless integration of this kind of scalability into this backplane. What you could do is have a line card which straddles multiple slots, right, to offer you that capability to scale beyond 400 gig per slot. But in the case of flex modulation or adaptive modulation, where you can actually flexibly change your modulation of your line, this will lead to further deloading of this fabric. This means that the overall capacity that you can utilize in your OTN switching infrastructure can be even less than what you actually invested in, right? So there's a lot of flexibility which is coming in the next generation DSP, but because you have a backplane before, a TDM backplane before the IP MPLS layer, there's a whole lot of inefficiency that's inbuilt in the current infrastructure. So how do we address this point? And the way we do it is we eliminate the OTN switching infrastructure. It's no longer necessary. We are basically unleashing the full potential of your photonic layer, including the flexibilities of the current and next generation DSPs, which are powering the coherent interfaces from your photonic infrastructure, and extending this without any hindrance, without any restrictions of a backplane between the photonic layer and your IP and PLS layer. So very, very seamless, very, very simplified network architecture that doesn't incur any complexity or restrictions in terms of getting the full flexibility and scalability of your photonic layer. Okay. I just wanted to, again, maybe before I proceed, so I want to talk more about this piece, right? This, what I've shown here, this very intriguing future 600 gig, 100 gig, 1.2 terabits. So you've heard from your vendors a lot, I'm sure, about adaptive modulation or flex coherent, right? These are industry terms, and which basically means that your line cards of your photonic infrastructure, they can flexibly change the modulation scheme. So no longer are you tied down to one specific line card for one modulation scheme. You can basically choose to modulate your line to many, many different kinds of modulation schemes, right? From BPSK, QPSK, blah, 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 to 16.4QM. And this corresponds to different line rates in your coherent line interface. That's fairly standard. Okay, every optical vendor worth his salt is capable of supporting this. In Cisco, we go one step further. Okay, we are able to combine any two modulation schemes in a single line interface into a single carrier, which means that we can vary the bits per symbol, and on top of that, we can change the baud rate to the symbol rate or the baud rate to ensure that you have the same line rate coming out of your coherent interface. And that corresponds essentially to the flexibility in determining your spectrum size, your spectral width. Why is that important, you may say? So again, perhaps a very technical chart, but this rectangle and these lines correspond to 6,000 states, where with the hybrid modulation I spoke about, we can vary the bits per symbol and vary the spectral width to support 6,000 different positions, which means that we can adapt and optimize the line interface to give you the best performance and the best reach of any interface that you encounter or that you have in your network. And I would like to contrast this with these red dots that you see here. These red dots basically correspond to the combination of bits per symbol and the baud rate that other vendors support today. So today we are able to support 6,000 states, whereas what's available from the other vendors is extremely limited in terms of allowing you the flexibility to optimize your line interface, right? And this means that you can optimize in terms of the span from a metro application to long haul to even submarine applications on the same line card, on a single line card. And this is an example of how we utilize that, right? So this is a mesh network. I find that this is the best way to illustrate the use case. A mesh network where you have services, and in this case it's a 600G service from point A to point B. And then the modulation of choice is 600 gig, which corresponds to a 64 QAM, a very big constellation. I'm sure you're aware that 64 QAM has a very high OSNR margin, so you need to have a very good OSNR to carry it over significant distances. So if you have, for example, a network fault, and you try to restore the service over, and typically it's over a longer distance, over more amplification stages, you'll find that very quickly your OSNR is much below the threshold of your back-to-back OSNR, which means that it's not feasible. And the only way that this will be feasible is if you were to deploy regeneration. And regeneration, as you know, is bad news. It's CapEx, it's complex, and you have to have these regenerations at strategic points in your network, and it's very, very difficult to predict how and where the fault will occur. So it's just not a scalable solution. And this is typically the case when if you have adaptive modulation, pretty much this is where you are stuck with. You just cannot restore the service unless you have expensive regeneration resources in your network. But what we're able to do is that with our solution, with a very flexible transponder solution like our NCS 1004 and a very advanced impairment-aware control plane, we are able to understand that we can still restore the service by provisioning a media channel with 2 carriers at 300 gig at 8 QAM potentially. So this is an example. I use it to illustrate a concept that you can restore the service on additional spectrum that you have in your restoration path without regeneration. But that's contingent on having a very flexible transponder, a very powerful DSP that allows you to trade off between performance and different modulation rates, right? So that is why the importance of a powerful DSP makes sense. And this is the platform which we feature the hybrid modulation with flex coherent adaptive modulation. NCS 1004, it's possible to deploy this as the client infrastructure for core applications together with a CDC ROADM, for example, our NCS 2000 in Cisco. And this is the architecture that service providers such as PLDT, which Muthu has referred to, this is the architecture that is being deployed in service providers' networks like PLDT, for example. And on top of this, because of the the very flexible DSP that's inbuilt into NCS 1004, we also have references in subsea applications, submarine applications. For example, there's in ARNet and Superloop, we have deployed over 5,000 kilometers of submarine fiber. We work a lot with the web OTTs. I'm sure without naming names, you know who they are. And this is across Trans-Pacific and even between North and South America. So we also have references for submarine cable applications, and all on the same line card on the NCS 1004. So this is just to illustrate the kind of power and flexibility that we have inbuilt into the NCS 1004. So in summary, I would want to remind you, and the key takeaways are that the bulk of the traffic is IP. It's easy to say, most of us realize this, but when it comes to actually deploying, it's surprising that the architecture that actually gets deployed is very different from the realities that we go through in our daily lives. So this is something that's important to bear in mind, that the best aggregation solution for IP is still IP. And we want to remove the unnecessary layers, the redundant layers, that is a legacy from the old TDM days. Those days are gone. We need to move forward, and we want to consider the most efficient and streamlined architecture for IP traffic. And in the metro, it's extending this kind of scalability and efficiency is very simple in the form of currently DCO optics. We will be going with 400G ZR, ZR+, for more scalability to 400G coherent in the metro, and in the edge and the core, where distances are more challenging, you need to leverage the most powerful DSPs, which allow you to trade off between the best performance and the best scalability in terms of your channels. Okay, so these are the key points that I would like you to consider, and I look forward to more interaction with you to cover in more details any questions that you may have with regards to the solution and architectures presented. So thank you very much for your attention.